I'm demonstrating a non-volatile forensic acquisition using Linux tools in a Docker environment. What we have is a simulated suspect system, a forensic workstation, and a shared evidence volume. Generally speaking, I had some confusion about what really happens during imaging. We have the theory, watch the videos, and you're like, okay, but how do I know if I'm actually changing anything on the original media, storage media, and how do I know if the image that I'm creating is, unchanged and exact copy? So, and doing labs like this helps conceptualize or visualize what's going on. Okay, so break it into steps. Perforation. Before touching anything, we ensure that we have, in my case, containers, and that the evidence is existing. So, all right. So I have two containers: forensic and suspect. Now let's take a look at the shared volume where the evidence is stored. Okay, and it's at this mount point here. So let's copy that real quick. Copy, all right, and then let's take a look at it real quick. And we'll list long form, whatever is human readable here, hit enter, and there we go. So root has read and write access, root group has read access, and other users have read access only. Okay, so now let's start the containers. So we're going to start them, and we use those names up there up top. And we should get a message. Yes, okay, they're started. Okay, clear it up a little bit. Okay, so in the lab environment, we want to ensure that we have the legal authority, or whatever environment, right? We have the legal authority, and we validated our tools, meaning we did some checks on them or some calibrations if required to ensure that they work at high consistency, and it meets our needs. We use clean power, meaning spikes and surges are not going to be good. So maybe we can also use an UPS device. If we have a power interruption, like say we have a large acquisition, and maybe something that takes hours or just a long time, and we have a power interruption or a spike or an outage that could corrupt the image, mess up the process during the writing process. So that's why stable power is important, and we have to plan for that. Okay. So step 2, identification. Let's access suspect container to identify the storage. Okay. So in this scenario, the storage, the suspect media is here in this suspect container. Okay. All right. So it's all in the evidence directory. So let's change that directory real quick and then take a look at it. Okay. Same information as the volume there. Now while we're here, let's take a look at the file, and it's ext formatted disk image. Okay, that's good. So exit there. Now let's take a look at the other container that is forensic. Okay, where we're going to do the work. Okay, and same thing here. We'll list it. Okay, and run the file again on that. And we see that we have the same formatted ext formatted disk image here. They share the same UUID. Okay. All right, now step 3, collection phase. We're in that workstation here, and the goal is to collect and image the suspect media without modifying it. And this is where I originally questioned something like, how do we know we're not altering the original media? So a gold standard is that we have a write blocker. Right? Hardware, there's also software write blockers, and in our case, it's read-only mounting, no auto mount, and we validated our tools, or verified that they're, we verified tool validation. Now, step 4 is the bit stream acquisition, or bit for bit, and we're going to use that dcfldd. And the tool is similar to DD, has some extra features. And so this command is kind of, okay, so what we'll do is, I left something out. Okay, so the input file is going to be at the evidence, located in the evidence directory, and that's the name of it. The output file, and we use that backward slash because we're going to add more lines to our command here. Output file is also going to be in the evidence directory, and we're going to name it forensic image.dd. Okay, and we're going to create a hash 256, and that hash is going to be part of this hash log, also in the evidence directory, and it's going to be in the hash.txt file. And then we're going to add some error handling. So let's say we have an error. If we don't do this no error, then it would stop at the first error that it encounters. So we don't want that to happen. And then we're going to sync, which is telling this tool here to pad a block with zeros so that the output image keeps the proper block alignment. And when you do that, it avoids having the output image smaller, for example, than the original whenever an error occurs. Okay, so fingers crossed. Okay, good. All right. So when we're thinking about the drives that we're using, the target or the source, some large files may cause a drive to throttle because of heating. So we got to ensure that our environment is prepared for that. Also, your destination media, the target media, must have enough space. All right, now step 5, we're doing the hashing and verification, and we're going to check the integrity, and we'll just do it manually here. So what we'll do is let's see what we got here. So we got the forensic.dd image, we have the hash.txt file that we created, and then we have our original suspect.img file. And let's go ahead and SHA-256 sum the image, and there's a hash right there. Okay, now let's check the copy that we created, and the .dd, and it's the exact same image or hash. And while we're here, let's look at the .txt file. Okay, and we see that they're all exact same values, and so they match, and that confirms that the image is an exact bit-for-bit copy. That's your mathematical proof, the integrity. And if the hashes don't match, then the acquisition it's not valid. So we have to repeat it, or go back and take a look at what we're doing. Okay, so now documentation. Documentation started from the very beginning. Maybe started with here's a scenario, like someone contacted us, and then tools used, versions of software, hash values, date and time, how we acquired, or the acquisition method, the environment we were in, and as detailed as we need to be. Some errors we encountered, or power events, and any hardware limitations. We didn't use a write blocker here, so and if you don't have a write blocker, you add that in your documentation. Closing, prepared the environment, identified the correct storage media, performed the acquisition, generated the hashes, verified the integrity, and then, okay, thank you for your time.